Welcome back to the lecture number 31. Today we are going to discuss a different topic which is called the energy transfer. As I told you briefly during our discussion on fluorescence quenching, like this is the broad topic of fluorescence quenching is the quenching of the fluorescence intensity by the presence of some other molecule which we termed as the quencher molecule. And the reason for the fluorescence quenching are of manifold. For example, the electron transfer is one of them. So, when a molecule is being excited to the excited state and the fluorescence comes from the excited state of the molecule. Now, if you have on electron deficient molecules or electron rich molecule present nearby to this fluorophore which is in the excited state, that the other molecule can donate one electron to the HOMO of that fluorophore, which makes the fluorophore to have a filled HOMO and the fluorescence will be deactivated immediately, or in other case it can take the excited electron from this fluorophore when the other molecule is electron deficient. Right. Similarly, this energy transfer is another case of the fluorescence quenching. Right. I can describe this energy transfer as one of the case of the fluorescence quenching. For example, like if you add some kind of molecule, then the emission intensity will decrease of the original fluorophore. Right. That excess of energy could be transferred to the other molecule, and that may create a new emission band of the other molecule. Let me write point by point. So, what I was trying to tell you is that you have a molecule, I named this molecule as D, and this molecule is in the excited state. So, it is D star. So, in absence of any other thing, this molecule will going to give you emission or fluorescence, right, and you can record the fluorescence intensity as a function of wavelength, emission wavelength, which is nothing but the fluorescence spectrum or emission spectrum of this particular molecule. Now, consider you have another molecule present in the solution. That molecule I write as A, and the result is that this molecule is being deactivated, right, and simultaneously these other molecules is getting excited. Now, here this has a different emission maxima. Let us say this emission lambda emission maxima or D, but this molecule will have a different emission maxima, lambda emission maxima of A, right. So, I can have, so as a result what you will see the fluorescence in now if I now may plot, right, this is my fluorescence intensity I, and then this is my wavelength lambda. So, initially when there was no A molecule, what you would have seen is that this is your fluorescence intensity, and this corresponding maxima is your lambda emission maxima of D. As you are adding this A molecule, then this fluorescence intensity will decrease, but a new fluorescence will appear like this way. If you add more A, then this fluorescence will further decrease, and in this new fluorescence intensity will be much more, and if we add further, it will be something like this. So, this new emission maxima is because of the A, not because of the D. So, this is lambda emission maxima of A. So, now if you look at this wavelength, right, you will see that fluorescence is quenching, but in this particular case here at this particular wavelength the fluorescence is actually increasing also. So, So, this is a special type of thing, right. So, just looking at, I can simply tell that here this molecule means this D star, the energy from D star is getting transferred to A, so that as a result that D is getting deactivated. Now, D is in the ground state and A is now in the excited state. So, by denoting with star, that means this D star is my energy donor and this A is my energy acceptor. So, simply we write this as donor and this as donor and this as acceptor. Right. Now, question is that how the energy is getting transferred, right. So, I can think of a simple pathway by which the energy is transferred. Let me write this as D star is getting converted to the ground state of the donor and plus the emitted photon which is h nu, right. So, I can write D to D plus h nu, I can simply write that, and then I can write this h nu is somehow being absorbed by this A molecule to make this A from the ground state to the excited state. So, I have first radiative emission of this photon and this photon is being absorbed again by this acceptor A. So, this is a two step process and this is known as radiative energy transfer. So, I can write this as case 1 radiative energy transfer, and this is a two step process. Now, just looking at this mechanism as I have written here, it is evident that if the donor quantum yield is high, right, that means, right, the non-radiative rate constant is much higher than the non-radiative rate constant. So, this process must depend on the quantum yield of the donor. Again, if you look at this, you see that this emitted photon has to be absorbed by this A, and that clearly tells me if I have more A present nearby the D, then this process, right, then these processes are more feasible, right. So, it also directly proportional to the concentration of A molecules present in the solution. If you again look at this diagram, automatically you understand that the emission wavelength of this donor must be very similar to the absorption of this acceptor, right. So, I can write these three different conditions over here. So, the condition number 1 is the fluorescence quantum yield of donor. 2, I can write the concentration A, and 3, I can write that overlap of emission. So, like these are the three conditions. If the fluorescence quantum yield is more, then obviously the emitted photons will be more, and then concentration of A is more, then the possibility of the emitted photon will be absorbed, this is also more, and then the third is the overlap of emission of D with the absorption of A, right. If these three things satisfy, then the efficiency of this energy transfer will increase, right. Let me this the point number 1 and point number 2 is easy to understand, but let me elaborate this point number 3. For example, let us say this is the absorption spectrum. Let me draw first. Let us say this is the absorption spectrum of the donor. So, I will just write here abs of donor. Depending on suppose you are exciting at the maxima. So, here is your lambda excitation, right. Then you will get the corresponding emission spectra of this. Let us say this is your emission spectra of the donor, right. You see, I have drawn as a mirror image, just because I just assume that here in the excited state there is no structure change in this molecule. So, mirror image rules holds good in this case. Now, if I use another color and draw the absorption spectrum of the acceptor, let us say this is the absorption spectrum of the acceptor. Now, you see the photon which are emitted at this wavelength, this wavelength, this wavelength cannot be absorbed by this acceptor, right, cannot be absorbed by this acceptor. One of the condition is that the delta E has to be matched with the incoming photon h nu, right, that should match, otherwise it is not possible. So, this is my absorption spectra of the acceptor. So, it is not possible, right. However, if the absorption spectra is not like this, but it is like this, this is absorption spectrum of the acceptor. In this case, what you can see that the photons which are emitted at these wavelengths starting from here to here, the absorption of this A is actually matching. There is a certain probability that these photons will be absorbed. Obviously, the absorption cross section at the different wavelengths will be different. So, the probability of absorption of the different h nu will be different, but there is some probability, there is a probability of the absorption. So, what you can tell that this common area, if this common area is large, then the emitted photon has a good probability for the absorption by this acceptor A. If this shaded region is small, then the probability that the emitted photon will be absorbed by this acceptor will be less, and this shaded region is known as spectral overlap integral and denoted as J nu bar. So, this J nu bar just is a inverse of the wavelength, right, and usually the unit we refer this as a centimeter inverse, and the expression for this that should contain the absorption spectra, the emission spectra of the donor and the absorption spectra of the acceptor, right, and this is generally evaluated as integration 0 to infinity, right, fluorescence spectra or emission spectra of donor. Obviously, this is plotted as a function of wave number. You can, I already discussed that you can change the units, right, you change from the wavelength to wave number to frequency, whatever you want, right. So, I am just using here the wave number into absorption spectra and epsilon, the molar extinction coefficient is same, is just divided by the concentration into path length. So, this is just a epsilon, this is the same thing, epsilon of the acceptor which is plotted against nu bar d nu bar. Right. So, this is my overlap integral. So, here this number 3, this 3 point is telling me if this overlap integral j nu bar is more, then this is more favorable, the energy transfer is more favorable. Right. Considering all these things, if you now try to find out the fraction, let me write the fraction of emitted photon by d star, right, and consequently absorbed by A. So, that can be evaluated, and that is generally expressed as a small a, and then I should have all these things over here, right, in the expression. I am not deriving it, I am just writing the expression, but all this one, this one, this one, everything should be present in this formula. Right. So, this is equal to 1 over phi d 0, where this phi d 0 is the quantum yield of the donor in absence of, I should write somewhere, I will write it. So, 1 over phi d 0 C A, this is concentration, and this is that path length, right, of the sample, and then integration 0 to infinity f d nu bar epsilon a nu bar d nu bar, where phi d 0 is fluorescence quantum yield of the donor in absence of the acceptor, and C A is your molar concentration of A, and L is the thickness of the sample. Right. Now, I will tell you the another possibility. That other possibility is that you have excited the donor, but before the donor actually emitted the photon, the energy is transferred to the acceptor A. Right. So, in this case this is a radiative energy transfer, as I told you, and the other possibility is that non-radiative energy transfer, and this non-radiative energy transfer is a one step process. Right. So, let me show you that. So, the other option is d star was there, and in presence of A, this d star become d and A become A star, and this is fall under this category of non-radiative energy transfer, which is a one step process. Now, obviously, I have to discuss about that what are the variables on which this non-radiative energy transfer depends. So, if you look at here, obviously, it depends on the lifetime of this donor, because if the excited state will remain there for a longer time, then only such kind of interaction is possible. For example, if you just excite and immediately come back, then there is no time for the interaction with this molecule. What kind of interaction? That is also important, that I am coming after few minutes. But what you understand is that the rate of non-radiative process must be low, so that the molecule will stay for longer at the excited state, then only the interaction is more favorable, right. If it is immediately come back, then interaction is not that favorable, right. So, it depends on the quantum yield, because that also depends on the radiative non-radiative pathway, and it depends on the lifetime, because it is the same thing, right, in absence of the acceptor, right. It also, now here it is not like that photon is emitted, right, and that photon is being absorbed by this A. So, the concentration, that how many are present, that is not important. The important parameter in this case is that, because they have to interact, this D and A, these two have to interact with each other. So, the important parameter in this case is how close are they. If they are far apart, then obviously for any kind of interaction, I will discuss what type of interaction it is, but if the distance are far apart, then those interactions are not feasible, as understandable. Okay. If they are close by, then obviously those interactions are feasible. Right. So, let me proceed by telling you that both this donor and this acceptor, right, they are dipoles, right. In rare case, they are not dipoles, right. I mean that they have some permanent dipole moment. That same dipole moment I was talking about when we are discussing the solvatochromic effect on the fluorescence. Like it has a dipole moment of mu d in the excited state, mu d in the ground state, they may be same, may be different, but in most of the cases they have this dipole. So, in this case the D has a dipole, or D is a dipole, and this A is also dipole. So, there is a possibility of dipole-dipole interaction. If I now describe this situation, this D star and A is as my initial state and D plus A star as my final state, this transformation from the initial to final must be accompanied with some perturbation, and that is the interaction between this donor and the acceptor, right. So, if I write the wave function of this initial state as psi I, which is psi D star psi A, and the wave function of this final state as psi f, I am just writing as a product of this wave function of D and A. So, in this case this is psi D psi A star, then I can write that particular transition, right, that means I to F, right, or I can write this probability of I to F. So, this is written as psi I, that is my perturbation, psi f, right. Now, question is that what is this H? As I said that they are dipole, and nobody stop us to tell that this is a Coulombic type of interaction. So, if I take this H as a Coulombic type of interaction, let me write that. So, here it is my H is Coulombic interaction, and in this case I will simply write this as H C, right, Coulombic type of interaction. So, this rate constant of this energy transfer K E T will be given by psi d star psi a h c psi d psi a star square, right. So, this will be my rate constant of this energy transfer. Now, the interaction energy between the two dipole, right. Now, let me talk about this this Coulombic interaction. So, the interaction energy between two dipoles, here I said that one is mu d, another is mu a, one is for the donor, another is for the acceptor, right. So, that is proportional to mu a mu d by r cube, and one factor f theta, which actually tells me about the relative orientation of these two dipole, right. So, it will have such kind of form. That means, this k T, the rate constant of this energy transfer, right, I should write as psi d star psi a mu d by r cube f theta psi d psi a star. So, here you see this r cube term is over here, and here is a square term. So, whatever it is, whatever the expression is, what I will get is this is proportional to r to the power 6, whatever the other term is present over here. I will get that this k E t is proportional to 1 over r to the power 6. That means, here you can see that the distance between the donor and acceptor is really one of the important parameter to decide about this fate of the energy transfer from d star to a to d to a star, right. We are going to see obviously the full expression. So, and as I told you, this also should depends on this f theta, right. This is also important, that is the relative orientation of the two dipoles, right. Now, if I write the complete expression, right, it will look something like this. This kappa square by, I will define this term, tau d to r to the power 6 phi d, right, and then there is some constant which I am not writing over here, and then integration 0 to infinity f d nu bar epsilon a nu bar d nu bar. You see, as I have commented, it depends on phi d, it depends on tau d, it depends on the distance, it depends on this overlap integral. Obviously, it has to depends on the overlap integral, because the energy should match, otherwise it is not possible. So, it depends on the overlap integral, and it also depends on this factor kappa square, where this kappa square is known as the orientation factor. Now, considering that obviously this tau d I should write as tau d 0, because this is the lifetime of the donor in absence of the acceptor, right. And obviously, I should also write this phi d as phi d 0, because this is the fluorescence quantum yield of the donor in absence of the acceptor. So, this whole equation, right, can be converted in a small equation if you consider the fact that here this is a constant term, this tau d 0, phi d 0 is a constant because this is a property of the donor. This overlap integral is a constant for a particular pair. If I define this is my D, this is my A, then overlap integral has to be constant for a particular solvent, right. So, all these things are constant, right. Only this kappa square is not constant because it depends on the relative orientation of the donor. Donor is like this, acceptor is like this, kappa value is different, donor and acceptor like that, kappa value is different like this. So, see this kappa square, right. So, I can convert this equation as kappa square, and obviously R is not a constant because the distance between the donor acceptor can change, can vary, by r to the power 6. I deliberately also take this tau d 0 over here, right, and rest of the things are constant. Okay, let me stop here and we will continue our discussion on next day. Thank you very much.